The airspace above us is clogged with millions of daily commercial, private, and military flight paths. Isolating a genuine anomaly within this dense web of global telemetry requires aggressively filtering out the noise. This is the exact operational hurdle facing the Galileo Project. By deploying custom-built multi-sensor observatories, their goal is to establish a rigorous, systematic, and transparent search for unidentified anomalous phenomena, or UAPs. But local sensors possess finite ranges. Spotting anomalies within an immediate, localized field of view requires immense luck over vast atmospheric volumes. Project DarkTrack proposes a software upgrade, moving localized observatories from a passive observation stance into an active, radar-cued hunting framework. By tapping into macro-level radar networks, the software can filter out over 99% of conventional aerial clutter in real time. This guarantees that when ground-based optical sensors are finally deployed, they are locking onto high-probability targets. The first phase of Project DarkTrack focuses on its data ingestion architecture. The system pulls in two continuous, overlapping telemetry streams over a specific geographic region. Stream 1 tracks the knowns. This is real-time ADS-B transponder data, ingested through commercial APIs or direct SDR receivers. This layer reliably broadcasts the discrete ID, altitude, velocity, and precise trajectory of cooperative conventional aircraft. Stream 2 tracks the physicals. This utilizes unclassified primary radar data, pulled directly from feeds like FAA System-Wide Information Management or atmospheric NEXRAD networks. Primary radar does not require an aircraft to broadcast an ID. It simply proves the existence of a solid, moving physical mass bouncing a signal back to the receiver. While high-fidelity military radar arrays possess greater tracking capabilities, that data is heavily classified. Project DarkTrack explicitly begins its proof of concept by strictly utilizing publicly accessible, unclassified civilian APIs. By layering these two separate streams over the exact same airspace, the architecture creates a real-time comparative map. It tests what is legally broadcasting its presence against what is physically flying through the sky. Processing this map requires the cross-correlation engine, a high-speed spatial sorting algorithm. It applies bounding box tolerances, comparing the coordinates of a primary radar return against the nearest ADS-B telemetry ping. When a radar mass perfectly matches an ADS-B ping within that bounding box, it triggers a match classification. The engine classifies these objects as known traffic and deletes them from the queue to free up processing power. But if a primary radar return tracks a solid, moving mass, and the bounding box detects zero corresponding ADS-B signal, the system triggers an anomaly classification. These silent, uncooperative objects are immediately flagged by the software as uncorrelated targets. This exact mathematical subtraction, stripping the known telemetry away from the physical radar returns, is the mechanism that isolates anomalies from the intense volume of modern aviation noise. Primary radar does possess a significant vulnerability. It frequently tracks biological false positives, such as large avian flocks, as well as consumer drones operating without transponders. To mitigate this, Phase 2 passes all uncorrelated targets through a machine learning filter trained on kinematic profiling. It measures movement against biological parameters. A transponderless mass steadily traveling at 40 knots aligns with an avian flock. The machine learning engine automatically dismisses these low-threat targets, tightening operational focus. Conversely, an uncorrelated target might exhibit sudden high-G accelerations or execute instantaneous transitions to supersonic velocities. This distinct kinematic behavior falls far outside biological or conventional aircraft limits, immediately triggering a high-priority system alert. Training models to confidently make these distinctions requires processing massive datasets of historical primary radar against archival ADS-B flight logs to establish rigid baseline normals. This machine learning layer acts as the final gatekeeper in the software, ensuring that local observatories never waste critical hardware cycles on birds or weather balloons. Verifying an uncorrelated target in a software environment is insufficient for scientific proof. The ultimate goal is physical observation and high-resolution optical data capture. Phase 3 introduces the automated hardware handshake. This is an automated protocol that securely bridges the DarkTrack software engine with the localized physical observatories. Once a target clears the machine learning filter, the engine mathematically extrapolates the forward trajectory and velocity vector of the anomaly. Simultaneously, the system queries a geographic database containing the locations of all active Galileo Project optical arrays. The trigger mechanism is strictly geographical. If the extrapolated vector of the anomaly enters the operational line of sight of any ground station, the software acts. The API middleware instantly transmits an automated slew command, feeding exact coordinate vectors directly to the local station. The localized pan-tilt-zoom optical array rapidly swivels, autonomously locking onto the extrapolated coordinates to execute continuous visual and infrared tracking. This direct hardware handshake completely removes human latency from the tracking process, flawlessly synchronizing macro-level radar detection with micro-level optical verification. Marrying wide-area macro telemetry with high-resolution localized sensors transitions the Galileo project out of a passive observation posture and into an active, targeted hunting framework. Phase 4 of the roadmap looks even further ahead. Successfully validating this data pipeline on unclassified civilian APIs provides the academic leverage needed to petition for constrained access to higher-fidelity government radar data. Securing research-focused access to classified networks like NORAD would drastically expand the system's tracking capacity, allowing the project to hunt kinematically extreme anomalies operating at much higher altitudes. The end result is a vast, interconnected network of optical observatories resting idle, perfectly synchronized, and waiting for the exact coordinates of verified targets. By aggressively filtering out the immense noise of conventional aviation, Project DarkTrack guarantees that the moment a genuine anomaly arrives, the instruments of science are already locked on and recording.